All right, so what we can continue with here is our Lewis structures, our covalent Lewis structures. And now we have we're going to start having a few more exceptions, right? We had our rules to start, now we're going to start getting some exceptions. So if we start looking at BCl3 or BEF2, right, what we're going to have is an incomplete octet, okay? So we have a couple of exceptions where boron and beryllium, they don't really have a full octet, okay? Boron just is always unhappy, okay? It doesn't matter if it has 8 electrons or if it has 6 electrons, it's just going to always be unhappy. So what we end up with is that we're only going to give boron 6 electrons, okay? So boron to start, right, if we count our electrons, we would have 3 electrons from boron plus 3 times 7 for chlorine, right? That's going to be 21, 24 electrons total. So what we're going to start with is let's give us a skeleton. We're going to put boron in the middle because boron was listed first. We're going to do 2, 4, 6 there, so we've got 18 electrons left, and we're going to give chlorine the other electrons. When we do that, right, there's all of our electrons that are going to be drawn on this structure. And we would say, hey, boron's unhappy. But boron is always unhappy. It doesn't matter. It doesn't matter if it has 8 electrons or if it has 6 electrons. It's just always unhappy. So we're only going to give it 6 electrons. So we have 2, 4, 6 electrons there. Okay? Beryllium is kind of similar, right? Beryllium with BeF2 here, we would say, hey, that's going to be an ionic structure, right? But because we have a nonmetal and a metal, but beryllium has a relatively high electronegativity, especially for a metal. And so in this case, we're actually also going to draw a covalent structure, okay? So we would say beryllium has 2 valence electrons plus 2 times 7 electrons. That's going to be 14, 16 electrons total. We'll put beryllium in the middle, and then we'll put fluorine on. And then we'll give fluorine the rest of the electrons. And we realize, hey, beryllium only has 4 bonds, or 4 electrons, 2 bonds. It's not really stable. It's not really happy, right? It's kind of, like I said, beryllium is a metal with a nonmetal, so we would kind of say that it's going to be an ionic structure, but it also has a lot of covalent character. So we can draw it like this as well, okay? Again, we've said that the ionic versus covalent is a spectrum, and so we have, in this case, an ionic compound that we kind of draw as a covalent compound because it has a lot of covalent characteristics, okay? All right, let's move on to our next row here. Our next row is about our expanded octets, okay? Our expanded octets is that sometimes, right, when we have lots of elements, we can force certain elements to form extra bonds, right? Normally, we can only form 4 bonds and have 8 electrons around an element. But sometimes, right, we'll force that central atom to have extra electrons, okay? And we'll talk about why that is in a second. Let's go ahead and look at this one. It's SF6, so sulfur would have 6 electrons, plus fluorine, so 6 times 7. 6 times 7, I think, is 42. Is that right? I think that's right. Plus 6 more, that's going to be 48 electrons. So when I draw this, I'm going to put sulfur in the middle, and I'm going to put fluorine around it. And in this case, I'm going to draw 6 bonds from sulfur to fluorines. Okay? Sulfur is in the 3rd period. Okay? It's in the 3rd period, so it has d orbitals available. And fluorine is the big pig, right? Fluorine really, really, really wants to have 8 electrons. So rather than sharing with other fluorines, it's going to force sulfur to share, okay? So it forces sulfur to share, allowing fluorine to have 8 electrons around it. So once we put all of our electrons on here, right, we should end up with 6 lone pair electrons, so 3 lone pairs on each fluorine, plus 1 single bond from each fluorine to sulfur. In this case, we have an expanded octet, and sulfur has 2, 4, 6, 8, 10, 12 electrons around it. That doesn't seem stable. It is not as stable, but because fluorine is the big pig and it really, really wants that extra electron, it gets a lot more stabilized when it has those extra electrons, right? When it has 8 electrons around it. And so it can force sulfur to share and have up to 12 electrons around it, okay? So for our expanded octets, we can have up to 12 electrons around them. And when can we do expanded octets? We have to have, right, fluorine or chlorine bonded on there, okay? Okay, so fluorine or chlorine has to be the one that are forcing us to form these expanded octets. And the central atom, absolutely has to be third period or lower. Okay? It has to be the third period or lower. All right? Okay. Let's look now at our multiple central atoms. Okay? In our multiple central atoms, right, we are going to have multiple atoms that are on the center. Okay? So we can do our exact same steps, but now we have to be a little bit more careful when we build our skeleton. So let's start first off just counting our electrons. So carbon, we have 2 times 4 plus 6 times 1 for hydrogen. That's 6, that's 8, that's 14 electrons total. Now in this case, right, we're going to put carbon in the middle. Hydrogen is always going to be on the outside, and it will always have only 1 bond. So we will put carbon in the center. We're going to build our carbon to carbon in the center here, and then we'll put our hydrogens on the outside. Okay? Once we do that, now we see, okay, 2, 4, 6, 8, 10, 12, 14 electrons. That's all of my electrons. Okay? So in this, when we build these multiple central atom ones, right, we're going to see that oftentimes, right, carbon will be in the middle. It likes to form 4 bonds, right? Hydrogen will always be on the outside. The other thing that we're going to notice is that when I have something like this, where we have this OH, okay, oftentimes, right, the way that I write this formula is kind of hinting at what the actual structure is. So we're going to have some sort of structure that has an O and an H on the end, okay? So hopefully we can try and fill these in, all right?